In our discussion of angular momentum, we talked about how the angular momentum of a single object can remain conserved even though its rotational inertia is changing because its angular velocity will change in tandem. But we didn't talk a whole lot about how the angular momentum of a system can be conserved. So we're going to see a couple of examples of that here. We're also going to start to explore a little bit more of an unusual aspect when it comes to angular momentum. Now we're going to start this off by looking at a little scenario. So let's say we have this ball with mass m that's traveling at velocity v naught b, that b just stands for ball, and it's going towards this rod, and the center of the mass of the rod has been labeled. It's just there in the center. It's got mass m, and it's initially not moving. And let's say this is somewhere far out in space. There are no external forces at all on this system. Well, what's going to happen as this ball comes in and then eventually strikes the rod? Well, we already know because we've done these sorts of things before back when we talked about linear momentum, and that is that the linear momentum of this system should stay conserved. But additionally, we also now know that the angular momentum of this system of two objects should stay conserved. So let's make sure this actually works out. Well, once they strike each other, or let's say before they strike each other, they're going to have some initial linear momentum, each object, and both of them are going to have some initial angular momentum. But the thing is, though, is that the linear momentum of the rod is zero because it's not moving, and the angular momentum of both of these objects is also zero because they're not rotating. So that we know that the initial linear momentum of the system is just the linear momentum of the ball, m v naught b, and the angular momentum of the system is zero, initially speaking. So now let's say, okay, well now they've collided, and now they basically rebounded. They're going in opposite directions, and we could say, all right, well, let's now look at the angular and linear momentum of these objects after this collision, and we would see that, oh, okay, that the linear momentum of the system would just be the linear momentum of each of them add together. They would have new velocities here, but their combined linear momentum must equal the initial linear momentum of the ball. But the angular momentum of the system is still zero because neither object is rotating. So everything appears to be a-okay. This is all good, pretty straightforward. But now let's just say we change the scenario a little bit so that the ball is no longer hitting the center of mass of this rod. It's instead hitting above that center of mass. In fact, it's going to hit basically the very top portion of the rod. What's going to happen now when the two collide? Well, first off, let's once again write out the conservation of linear momentum, the conservation of angular momentum equations, and let's go ahead and figure out, okay, what's the linear and angular momentum beforehand? And we would see that, okay, there really shouldn't be much of a difference here, right? Nothing has changed so far. But what about after they collide? Well, after they collide, the rod is not just going to be moving to the right. It's also going to start rotating. We just know that from practical experience. If you hit something off the center of it, it's going to start spinning as it goes outward. And this is going to continue as it continues moving away. It's going to continue going end over end. And so let's say, all right, well, we're going to look at the angular momentum and the linear momentum of both objects after this collision. And the linear momentum is going to be exactly the same as it was in the previous scenario. Now, the velocities may be a little different now, but they're still going to be conserved. Everything is a-okay here. But if we look at the angular momentum, well, the rod is rotating now. And the ball is not rotating. There's nothing to cause the ball to rotate, so how can the rod be rotating? Because now it has angular momentum, even though the system didn't have any angular momentum initially. So what exactly is going on here? And this might lead us to believe, okay, maybe this particular number right here, 0, maybe that's not correct. Maybe the system had angular momentum before the collision. So let's start to think about this. This ball initially had linear momentum, but initially had its mass and velocity. It was moving toward the right, but it was no longer going directly towards the axis of rotation of that rod. Because remember, the rod is going to naturally go around its center of mass since there's no external axis holding it in place at some point. So the center of mass is going to be this axis of rotation. So it's not going towards the center of mass, and so therefore angular momentum will result. So we saw that when there was some axis of rotation that was separated from this path here, that all of a sudden the system seemed to have some initial angular momentum. And we're going to go ahead and say, okay, this was the axis, and this is some distance r from the axis to the path that is going here. And we could say, all right, well, if this object had angular momentum, which seems bizarre, admittedly, but let's just go forward for a second, that would be L was equal to I omega. But what exactly would I and omega be here? Well, it is we could say a particle moving in a circle around some external axis here. So that would be, I would be just mr squared, where m would be the mass of the ball and r would be that distance here. And the angular velocity, omega, is the same thing as v over r. So we're going to go ahead and stick that in as well. But when we do this, we see that one of these r's cancels, and we are left with, I just rearranged it here, rmv. And additionally, one important point here is that we're going to go ahead and make sure we clearly label that this is perpendicular here, that this path is perpendicular to this r, so that we can say this is v perpendicular. So I'm going to label v perpendicular here as well. But what is mv perpendicular? Well, that's the same thing as the linear momentum perpendicular to this r here that separates the axis from this path. And this is actually the equation for the angular momentum of an object around an external axis of rotation. Once again, just go with me for a second. So this is L, which is this angular momentum in kilograms meters squared per second, is equal to RP perpendicular. So R is the length of this lever arm, but that lever arm really is just the distance separating the axis of rotation from that trajectory. And P, the linear momentum, is basically the momentum perpendicular to that lever arm. So we want to set up our lever arm so it is perpendicular to the trajectory. And then additionally, this is equal to rmv perpendicular, because usually we will have the mass and the velocity, not the p, so this is another way to write that, where m is the mass of this external object, and v is the velocity of this object perpendicular to this lever arm in meters per second. So now let's go back to this previous scenario. So the ball was coming in, hitting this rod above its center of mass, so above its axis of rotation, because the rod will naturally flow, naturally rotate around this axis. And we go ahead and just say, all right, well, we know that beforehand it must be equal to the combined linear momentums, combined angular momentums. But the thing is, though, is that we actually do have angular momentum from this ball before the collision. And that's going to be equal to r, that lever arm here, that distance between the axis and the trajectory of the ball at a perpendicular angle here, times the mass times the velocity of the ball initially. And after they collide, once again, we are going to have a new setup, and we're going to see that not only is there actually angular, well, this, by the way, linear momentum hasn't changed at all, but not only is there angular momentum of the rod, but even the ball has some angular momentum after the fact, because now it's moving with respect to this axis of rotation. Now, I didn't write an equation here, because technically speaking, you would have to combine the linear velocity of the rod and the ball to get that accurately, but we have the basic idea here, that there is some angular momentum beforehand and afterward, despite the fact that there is no rotation happening with either object before the collision even occurs. Now, there is probably a very good chance that this hurts your brain, because you're looking at this and going, okay, well, the ball is not spinning. How can it possibly have angular momentum? Well, the thing is, though, is that it may not have angular momentum about some internal axis, but it does have angular momentum about some external axis. So by labeling this as an axis of rotation, the system has gained angular momentum. And a way to visualize this is, let's go ahead and say, let's pretend that this is, zoomed in what we see, but let's say we zoomed out and this ball was actually traveling in like an oval-like pattern here or something. And we could say, well, technically, if we zoom in on this oval here, this part of its trajectory, that looks identical to this. And in fact, we cannot say that they are physically any different. Now, we can expect that this ball is going to continue going in a straight line, but technically speaking, that's physically no different than this scenario. So we can treat the ball as if it is orbiting or revolving around this external axis of rotation. So the object is still moving around the axis. Now, you might be thinking, okay, that doesn't make any sense. How can it be moving around this axis? But keep in mind, at this point here, it's going to have some angle, theta, and then when it gets to, for instance, this point here, well, that theta is going to be different. When it gets to here, that theta is going to be different. When it gets here, theta is going to be different. So we are still having a situation where the object is moving around an external axis. That angle, that angular displacement, is still changing. We just have to reformulate how we're thinking about this. Now, a really important point here, though, is that this is really dependent on the choice of our axis. If I put my axis over here, or over here, or over here, or over here, or wherever, that's going to change the angular momentum of the system. And you might think, well, okay, well, how does that work? How can the angular momentum stay conserved? Well, in doing that, you're going to be changing how the angular momentum is defined. You're going to be changing what is external and internal torques, etc. It will always work out that the angular momentum of the system remains conserved. So to help us think about this a little bit more, let's look at an example. Let's say that my dog Chewy, with a mass of 20 kilograms, runs at 10 meters per second and jumps onto the edge of a merry-go-round. So just like we see here, Chewy's going to run straight, she's going to jump on the edge of this merry-go-round, and the merry-go-round initially, though, is at rest on this frictionless axle. Okay, and we're going to go and say that the merry-go-round has a rotational inertia by itself of 75 kilograms meters squared, and that has a radius of 3 meters. And if she is moving perpendicular to a line connecting the axle to the edge as shown, so in other words, she doesn't jump onto this part towards the axle, she jumps perpendicular to the axle, what is the final angular velocity of this system? So, okay, make sure we fully understand. She's going to run, she's going to jump, land right here, and when she lands, that's going to basically cause a torque to be exerted on the merry-go-round. The merry-go-round will exert a torque back, slowing her down, and the system will start with her on it, spinning in a circle. So let's start reasoning through how exactly. Now, when I say final angular velocity, we're really looking for the magnitude here. Okay, so let's go ahead and say, well, the angular momentum of the system is conserved, so it's going to be the same initially as it is after this collision here. And what are the objects in my system? Well, I'm going to say, okay, the merry-go-round and Chewy are the two objects, so the angular momentum of each separated must equal the angular momentum of them combined after the collision, because after Chewy jumps on it, they're going to start moving together. So this is kind of like an inelastic collision here. I had two objects, and we're going to end up with a combination of objects moving in tandem. Now, if we look at this, well, what is Chewy's initial angular momentum? Well, that's just going to be RMV perpendicular, and we have all of those pieces of information. The angular momentum initially of the merry-go-round is 0 because it is not rotating initially, and the angular momentum of the two combined. Now, remember, we can figure out the rotational inertia of a system by just adding them together. So this would be equal to the rotational inertia of Chewy on the merry-go-round plus the rotational inertia of the merry-go-round itself, times the angular velocity of this system, because L is also equal to I omega. Now, one thing we want to note here is I gave you the rotational inertia of the merry-go-round, but what's the rotational inertia of Chewy when she lands on here? Well, she would be like a point on the edge of the object going around, so that would be equal to mr squared. And now we're just going to simplify this by we're going to move that part over to the other side, so we have omega is equal to RMV perpendicular over mr squared plus I of the merry-go-round. Stick in some numbers. 3 meters times 20 kilograms times 10 meters per second, all over the I of Chewy, which is 20 kilograms times 3 meters squared, plus the rotational inertia of the merry-go-round, which would be 75 kilograms meters squared. Let's go ahead and take our calculator out, punch this in, and we should be getting that the angular velocity of the system is 2.35 radians per second. So when she jumps on the lands, that is the rate at which it's going to spin. Okay, we're going to go ahead and stop there. Don't worry if you're having a hard time with this. We're going to practice this a lot in class, but I really want you to focus on the fact that angular momentum can still exist for an object that is not spinning as long as it is moving around, or at least in relation to, some external axis of rotation.